Hey everyone, in this video I want to talk about a couple of really interesting, really useful properties of group homomorphisms, specifically mapping properties regarding identity elements and inverses. But before that though, let's tersely recap what the definition of a group homomorphism is so that we can get the most out of those results when I present them. Anyway, for now, that's what you see there in blue. A homomorphism phi from a group G endowed with a binary operation dot to a group G prime endowed with a binary operation star is simply a mapping from G to G prime that preserves the group operation. More specifically, this is what we want to be true. Phi of A dot B needs to be equal to phi A starred with phi B for all elements in G. All elements A, B, and G. And the standard way of indicating visually that a group homomorphism is taking place is simply to draw two dimensional regions, in this case for G and G prime, throw a little arrow in between, throw a little phi right above, and there we have an indication that group homomorphism is taking place. Now, this visual up top doesn't really illustrate the definition, but other visuals do, and so that's what you see down here at the bottom left of the screen. Suppose in G we pick two arbitrary elements, A and B, and form their product. A dot B. That's also in G due to closure, group closure. And now we know that phi A and phi B are both in G prime by definition of phi. Again, it takes elements from G to G prime, and moreover, G prime is a group. So phi A starred with phi B needs to also be an element in G prime. That's what you see there. But the key thing for group homomorphism is that A dot B must subsequently be mapped to phi A star with phi B. That's the key point. That illustrates that formula up there. Now, something interesting happens if phi is injective. If phi is injective, what that means is that there is a piece, a part, a subset of G prime that has the same internal structure as G. In other words, G is isomorphic to the image of phi. Moreover, if phi is injective and surjective, that means G and G prime have the same internal structure. And this picture on the left nicely illustrates this fact visually. The same internal structures means that two groups are isomorphic. Even if our homomorphism lacked injectivity and or subjectivity, it's still going to be the case, and these are quite easy to prove, that phi of G, the image of phi, is a group. Moreover, for any subgroup of G, proper or the full group G, phi of H, the image of phi, is a group. Now then, with this nice recap nicely on the table, let us now discuss those two interesting properties alluded to at the beginning of the video regarding identity elements and inverses. Just to add some pizzazz, put a picture indicating that homomorphism taking place. There we go. Now first interesting property, it turns out that the identity element of G will always map to the identity element of G prime. It's always going to happen for a group homomorphism. Secondly, you pick any element x in G, then phi of x inverse will always be equal to the inverse of phi of x for all elements x in G. So with that in tow, let us prove statement number one. Phi of x, where x is any arbitrary element in G, can always be written as phi of x times the identity element of G prime. Now I can also rewrite phi of x as phi xe, and using group homomorphism properties, that is phi x times phi e. By the way, I'm using dots as my binary operation here instead of a star, but I do that without loss of generality. Set those two red underlined expressions equal to each other and left side multiplication by phi x inverse, the inverse of phi x. So in one fell swoop, we get that the identity element of G always maps to the identity element of G prime. And that's our starting point for the second property proof. E can always be written as x times x inverse, so we stick that in there. Utilize group homomorphism properties to break up that left side into a product of two things. And now again, we utilize left side multiplication by the inverse of phi x. And that guy right there is the identity element of G prime. So the left side is just phi of x inverse, and the right side is inverse of phi x. So in one fell swoop, we have shown that a homomorphism always takes the inverse of any x in G to the inverse of the element that it maps x to. It's quite nice.